randomization. That's all it means. And the property, the key property that we have is in expectation. The expectation is over whatever randomness you used. So if you picked, some random training data point out of the million, then the expectation is over the probability distribution over what kind of randomness you used. If you picked uniformly at random from a million points, then this expectation is over that uniform probability. But the key property for SGD, or at least the version of SGD I'm talking about, is that in expectation over that randomness, the thing that you're pretending to use instead of the true gradient, in expectation actually it is the true gradient. So in statistics language, this is called the stochastic gradient that we use is an unbiased estimate of the true gradient. And this is a very important property in the mathematical analysis of stochastic gradient descent, that it is an unbiased estimate. And intuitively speaking, anytime you did any proof in class or in the book or lecture notes, wherever, where you were using true gradients, more or less you can do those same proofs, more or less, not always, using stochastic gradients by encapsulating everything within expectations over the randomness. I'll show you an example of what I mean by that. I'm just trying to simplify that for you. And in particular, the unbiasedness is great, so it means I can kind of plug in these stochastic gradients in place of the true gradient, and I'm still doing something meaningful. So this is answering that earlier question.